coordinator of the Human Powered Airplane project, and that's Stephen Wu, and that's Samuel Reyes. We're here to give you a brief presentation on who we are and what we do. First, we'll go over the background of Human Powered Airplanes in general, and then afterwards, we'll go over our project's own design along with organization. After that, we'll go into the projects we've done over the past few years, along with the projects we've done recently, and then we'll go over our budget. Finally, I'd like to hand this off to Mr. Wu, who will talk about the background of Human Powered Airplanes.
Thank you, Mr. Quinn. So as you can see, we are the Human Powered Airplane Group. Our main goal is to design an airplane that is capable of human-powered takeoff and flight. Since the 1900s, multiple attempts have been made at human-powered airplanes, with the first recorded flight conducted in 1921, with their design flying approximately a distance of 3 yards. The first true flight made by a human-powered airplane was done in 1961 by Sunpac, which was able to travel 70 yards. The most monumental event currently in human-powered airplane history was done in 1988 by MIT's Daedalus, which was able to fly 71.5 miles in under 3 hours. UC Irvine has previously had a contribution to this human-powered airplane timeline in 1989 and 1990 with their first two designs, and after a 25-year hiatus, the project has been revitalized with goals to finish building their HPA by summer 2015. I'll now hand it off to Mr. Reyes, who will talk about the specs of our plane.
Thank you, Ms. Wu. Some important specifications to note is that we have a 108-foot wingspan with a 4-foot chord, a propeller diameter of 12 feet, and a projected flight weight of 300 pounds with a projected flight speed of 17 miles per hour. Now I'll move on to organization. We have a centralized team, starting at the top with our project managers and chief engineer, then on to our team leaders who are in charge of various sections of the plane, and then to our members who can move freely between each team where work is needed. And now I'll pass it off to Mr. Wynn to talk about design choices.
Thank you, Mr. Reyes. So when we designed our Human Powered Airplane project, we did not want any external water brakes because we wanted to minimize the amount of drag in our airplane. We also wanted to have as little drivetrain losses as possible, so we went with a configuration where the drivetrain was in line with the pilot speed so that we could use a bell gear assembly instead of the usual chain gear assembly. And we also, which led us to having a cantilever wing along with a wing wall fuselage design. Because we had a cantilever wing design, we wanted to optimize our wing spar, and we noticed that previous human-powered airplanes that used a circular spar, which we noticed was not as optimized in bending in one direction. Instead, we went with a rectangular spar. However, rectangular spars have never been used in human-powered airplanes before, so we had to make our own. We did this by taking a MATLAB code that took in our flight conditions, flight loads, and then gave us an ideal carbon fiber layup schedule, which we then used to build up the spars. After we built the spars, we tested them and wrote them, and then compared them with what the MATLAB code predicted to deflect. And after a few trial and error runs, we finally got the MATLAB code to be extremely accurate, as you can see in the top left, top right for you guys. And which meant that the MATLAB code was accurate and that it was reliable enough for us to use. And so with that, we made all five of our, we made our 108-foot long wing spar. And also, we had to have we could not use a conventional tail design because with a wing wall fuselage, if we had a conventional tail design, the tail would be round. So we needed ground clearance, which is why we went with an H-tail design. And that design also came with added bonus of inducing less torque on the tail boom. Now, with all of our design choices already made, last year we went about making most of the structural components of the airplane. The top left, you can see us working on the fuselage frame, which is to house the pilot and its structural member that supports the pilot in flight. And then we also constructed a tail boom and the associated tail boom tail surfaces in the top center. And on the top right, you can see the plug that we made to construct our fuselage fairing mold, which we'll use to make the outer case that's around the pilot. And finally, last summer, we finished the structural components of our wing. You can see it there assembled in front of Engineering Gateway Plaza, being load tested. The wing was able to survive the load testing, which meant it is structurally sound and stable, and therefore good to use. With all the structural components finished, all we had to do left was to finish up clean up the airplane a bit, and then we would go to flying. And now I'll hand it off to Mr. Wu, who will talk to you about finish up what we did over the past few months.
Thank you, Mr. Wayne. So as you can see from the previous slide, we were able to prove that the structural members of our wing sections could pass our load test. After we knew that they were structurally sound, Faulkner was then evaluating ways to cover our structural members with our foam leading edges, as well as researching different materials that would heat shrink, that would shrink under heat to provide tension to create a shape that would conform to our airfoil. Winter quarter was spent fully covering all 5 of our wing sections with our foam leading edges, as well as performing more tests to completely cover them with our wing skin material. I will now hand it off to Mr. Reyes, who will talk about controls.
Thank you, Mr. Wu. With most of the control structures already built, our goal this quarter was to simulate how our control system would react during flight. In order to do this, we performed a deflection test on our tail boom, and we also tested our cable system to make sure that the elevator and rudder controls were working properly. And now to talk about fuselage and propeller, I will now pass it off to Mr. Wayne.
Thank you, Mr. Reyes. This quarter, we noticed that our center of gravity on the airplane was a bit too far towards the tail, which meant that in flight, the airplane would have a tendency to nose up and probably crash. And so we spent most of the fall quarter figuring out where to reposition the pilot so that our center of gravity would move forward more. And then in winter quarter, we went about actually changing the fuselage a bit and extending it, because if the pilot is going to move a bit forward, then the frame had to be a bit bigger to accommodate the pilot. And currently, we're still working on that. And now on to the propeller. For the propeller, last year we finalized our production method, which was to use a female molding method. And so in fall quarter, we made all the parts to make the rest of our propeller blades. In winter quarter, we seamed all those components together and made an actual propeller out of them. You can see me on the far left there, far right there, holding our full-size propeller, and it's 6 feet tall and it dwarfs me easily. As our propellers made, we decided to run a preliminary thrust test to see how much thrust we could get out of those propellers using our propeller test stand. We were able to get a static thrust of about 40 pounds, which was adequate for our purposes because we don't see drag of about 10 pounds in flight. We also decided on a propeller hub configuration because the propeller hub configuration on our propeller test stand was adequate for our use, so we decided to use that in our actual airplane as well. That ends what we've done in the past few months, and now I'll hand it off to Mr. Wu, who will talk about our budget.
Thank you, Mr. Quinn. As you guys can see in the pie chart above, this is our projected budget and its allocations for this year. The majority of the budget is diverted towards the completion of our drivetrain, as well as the logistics for our first test flight. The remainder of the budget is directed toward the full completion of all our sub-assembly components with a factor of safety of 1.5 to account for any design or any manufacturing issues that may occur. I would now like to introduce our plane design for this year. So our projected schedule for this design is to have all 5 wing sections fully prepared and wing skinned by mid-June.
And have our controls calibrated by early July.
We also intend to have our drivetrain installed with our fuselage and attachments fully ready by the end of July.
And finally, assemble and test fly our plane by August 31st.
That's our presentation. Any questions?